Hello class, so this is going to be the last video in this first series of videos, right? So the first lecture on this extra topic. In the previous video, we saw that it's very easy to determine whether two vectors are linearly independent. You just calculate their Wronskian, right? And finding the Wronskian now is way less work. Just okay, x1 is the first column of the matrix, x2 is the second column of the matrix. So very easy. Right? So very similar to what we did in chapter 4. Now we're finally at the point where we can define the fundamental set of solutions. The same way as we did in chapter 4. A set of n linearly independent solutions of x prime equals ax. Right? So again, homogeneous case. Right? And since we have n linearly independent solutions, we need n derivatives in the system because we need n equations. Right? So the number of solutions on the fundamental set of solutions should be equal to the number of derivatives, which is equal to the number of equations in the system. Okay? So if you have a system with 2 equations, you're going to need 2 linearly independent solutions. If you have a system with 8 equations, you're going to need 8 linearly independent solutions. Right? So again, suppose you have a set of n linearly independent solutions of the homogeneous system on an interval I. By definition, that is what we call a fundamental set of solutions on that interval. Same definition as in chapter 4. Okay. And as in chapter 4, we also have this existence theorem, which I'm not writing as a theorem, just as a note. A fundamental set of solutions always exists for some interval. And so again, since we know that there exists a fundamental set of solutions, it's going to be worthwhile for us to determine a way for finding the fundamental set of solutions, to finding n linearly independent solutions to an nth order system of linear ODEs. And then, as before, the general solution for the homogeneous case is just a linear combination of the fundamental set of solutions. Right, so let x1, x2, up to xn be linearly independent of the linearly independent solutions of this homogeneous system on some interval I. Then the general solution for this system is all possible linear combinations of these x sub i's and this is a general solution on this interval I in which these functions are linearly independent. So again, everything follows exactly the same, right? So following our example, right? And again, I wrote x1 and x2 instead of x and y. So we already verified that x1 given by this and x2 given by this are solutions to this system, right? We verified that for all real numbers. We verified that they're linearly independent for all real numbers, right? So the general solution for this system is given by all possible linear combinations, and the interval is all real numbers. Now, here let me add that for this I, all these functions also have to be, okay, the wording makes it so. I was going to say that all these functions have to be defined, but the fact that there are solutions on I already states that they're defined on I. Okay, so we're good, nothing to add. Okay. So you see everything matches the same, right? So now we know how to, if we can find a fundamental set of solutions, we know how to write the general solution for the homogeneous case. What if the system is not homogeneous? What if we have a system that looks like this system here, like system 2, where we have a vector x, vector g adding? Well, just as it worked out in the non-homogeneous case for one ODE, it's the same thing. All you need is to find the general solution for the homogeneous case, find a particular solution, add them together, and that's the general solution for the non-homogeneous case. So exactly the same theorem as in chapter 4. So now that we've gone over all this, we saw that everything generalizes nicely. Now the question is, how do we find, first of all, how do we find a solution to the homogeneous case? Once we know how to do that, we determine how to find a particular solution to the non-homogeneous system, and then we're done. We know how to find a solution to any non-homogeneous system in our particular form. Right? We're only considering first order linear ODEs in our system of equations. Right? But that's the idea. So that's what we're going to do in the next videos. We're going to see first, how do we find solutions to the homogeneous case? And then we're going to see how to find a particular solution.